Welcome to part 1 of Simple Harmonic Motion, SHM. So before we start with any exercises, I'd like to go through some of the basics. So the basic postulate of simple harmonic motion is acceleration is equal to minus omega squared x, where the minus indicates that the acceleration is towards the point of origin and x is the displacement, where omega squared is called the angular frequency squared. So if we look at acceleration being the differential of v, so v dv by dx, then we can set v dv by dx is equal to minus omega squared x. Now if we separate the variables, then we have an integral of v dv is equal to the integral of minus omega squared x dx. So integrating with respect to v, we get a half v squared, and integrating this side with respect to x, then we get minus omega squared x squared all over 2 plus the constant of integration. Now, in simple harmonic motion, at the maximum displacement, we call the maximum displacement the amplitude, and at that point you have zero velocity. So using these initial conditions, we can find the constant of integration. So substituting in those values, we find that we have minus omega squared a squared all over 2 plus c is equal to 0. So c is equal to omega squared a squared over 2. So this goes back into the equation that we first got from our integration and can be simplified and factorised to give v squared is equal to omega squared a squared minus x squared. Now, I've indicated that you need to learn this because you need to learn it. Quite an important point, an important derivation that you might need to be able to prove. Now this is a beautiful little derivation that takes you to the next step. This doesn't need to be learnt, but we'll show it anyway. So velocity is equal to plus or minus the square root of the previous result. So we can express velocity as dx by dt, and so we have this that can be separated and integrated. So if we separate the x's out and leave the omega where it is, omega is a function of time, then we can integrate with respect to x and we can integrate with respect to time. Now, this is actually an integral via substitution that can be done. Using the substitution, x is equal to a sine theta. So dx by d theta is a cos theta, so dx is a cos theta d theta. And when we use that substitution, then we get the following result. A squared minus x squared to the power of a half is equal to a squared minus a squared sine squared theta to the power of a half is equal to a cos theta. So using that and integrating, we get the following. Okay, so we get that the integral of d theta is equal to plus or minus the integral of omega dt. So theta is just omega t plus a constant of integration. And it's this constant of integration that, if you're familiar with physics, you'd call a phase difference. It's the difference in phase between two waves. The phase difference that we're talking about here is the distance between of the wave, or how out of phase it is, with a sine wave. So that can be used from our initial conditions. So if a sine theta is sine omega t plus alpha, then from our original substitution, x is equal to a sine omega t plus alpha. Okay, so that bit not as necessary to learn as the first bit, and in the next video I'm going to do a little example. Okay, if you are unsure, have a look at the video again and try and follow what's been done. The integration by substitution is part of the C4 course, so you might need to just have a quick look over that. Hope you found it useful.